We're now going to define the cross product of two vectors. So this is another sort of algebraic operation that we define on vectors. And just like the dot product, the cross product will have some really significant geometric properties as well. But in this video, we're going to focus on the algebraic definition of a cross product, and then just look at a couple examples and some of its algebraic properties, right? So let U be the vector U1, U2, U3, and V be the vector V1, V2, V3, right? So these are two vectors in 3 space. We define the cross product. So the cross product of U and V as follows. Here is how it's denoted. Now, we can't use the dot, right, to represent this product. So what we're going to use is the actual times symbol, or a little cross or X symbol, to represent the cross product of these two vectors, right? And the way we're going to define it, we're actually going to use a 3x3 determinant as a way to define it, because it's a nice way to remember how to set it up, right? And even though some people might have an issue with using a determinant as a way to define a cross product, I don't have a problem with it at all. There is an equivalence there that I think is fine. So this is how it's set up, and then we'll go ahead and write it down. So to find the cross product of these two vectors in this order, U cross V, that's how we will say it, U cross V, put the standard unit vectors in R3 in the first row, put the components of U in the second row, so U1, U2, U3, and then put the components of V in the third row, V1, V2, V3. And when we evaluate this 3x3 determinant using our expansion procedure, the result will be the cross product. Now notice, since our answer will have I, J, and K in it, it turns out when we compute the cross product of two vectors, we get a third vector, right? So let's go ahead and write this down, just so that you see what it looks like, right? But again, it's not something that you want to. I mean, I guess if you can see the pattern, because there is a pattern in the expression that we're going to write down. If you just want to use that expression, that's fine as well. But remember, when we're doing our cofactor expansion for a 3x3 determinant, this is what we do. We take our I, and then remove the first column in the first row, and we're left with the 2x2 submatrix U2, U3, V2, V3, and then minus J. Now remove the second column in the first row, and we're left with the 2x2 submatrix U1, U3, V1, V3, and then finally plus K times, and then delete the third row first column, and we have this 2x2 submatrix left, U1, U2, V1, V2. All right, and then to kind of finalize the expression, we use our 2x2 determinant formula. So I'm going to put the number in front of the I, because that's how we usually express the vector, right? We put the component in front of the standard unit vector. So here we will have U2V3 minus U3V2, that quantity times I. So this quantity is the first component of the cross product. Then we'll have a minus, so I'll bring down that minus. Then let's put the expression for this 2 by 2 determinant. U1V3 minus U3V1. And then finally plus K times U1V2 minus U2V1, right? And again, you might look in some scientific textbooks where this is literally how they say, okay, this is the definition of your cross product, and that's it. And that's fine too. The reason why I like to take it back to the 3 by 3 determinant is that it gives us this nice setup, right? Where, what if you miss the pattern here in the expression, because this expression, when it's expanded, is a lot more complicated than just filling out rows and then going through the expansion. But ultimately you choose, what works best for your mind, right? So this is the cross product, right? Now, in order to, I guess in some sense, illustrate probably one of the most important properties of the cross product, I want us to do something a little strange, right? So we realize now we have 3 vectors on our screen right now, right? We have U, we have V, and then we have this other vector. In fact, just to really hit home that this is a vector, here is it in the component form. So it's U2V3 minus U3V2, comma, and then I need the negative of this. Now what I'm going to do is I'm going to distribute the negative sign, and then it's going to make this term positive. So U3V1, and then this term negative U1V3, and then comma, and then here I'll just write down the third component, U1V2 minus U2V1, right? So yes, as I'm saying, we have 3 vectors on our screen. So I'm going to do something a little strange before we get into examples with numbers. I am going to take my generic vector U. So let's do this. Let's consider this calculation. I want to take my original U and do a dot product with what I got right here as my cross product, right? So I want to do this. I want to do U dot with U cross V, right? So remember the components of U were just U1, U2, U3. So I have to take U1 and multiply the first component in our cross product. So it's U1 times this quantity. So U2 V3 minus U3 V2. And then plus, take the second component of U and multiply the second component of the cross product. So U2 times U3 V1 minus, that should be a U, not a V. So U1 V3. And then finally, take the third component of U and multiply the third component of the cross product. So U3 times the quantity U1 V2 minus U2 V1. And then let's go ahead and expand and distribute the U1, U2, U3. And let's see what we have. So we have U1, U2, V3 minus U1, U3, V2, and then plus U2, U3, V1 minus U2, U1, V3 plus U3, U1, V2 minus U3 U2 V1. Now, let's take a close look. So we have a term here that's U1, U2, V3, right? Well, take a look at, let me underline this one. So take a look at this and take a look at this. These are exactly the same, except this term is negative, this term is positive. So they'll actually cancel each other out. Wow. Let's look at this term here. So we have negative U1, U3, V2. That looks like the negative. So this term here is the negative of this term here. So, they cancel out too. And I think you see what's going to happen. Look at this. So U2, U3, V1. And then here it is. We have our U3, U2, V1. So again, this term here is the negative of this term here. So they cancel out, right? So look at that. We came up with this definition for the cross product, right? Looks kind of messy, lots of letters. It's an alphabet and actually at alphanumeric soup, right? Numbers and letters. And then we took, just for fun, right? Because again, how is the finding the dot product not fun, right? It is fun. So you find the dot product of one of our original vectors, and it turns out that we get 0. So there has to be something significant for it to work out like this. It's just, and notice I did this without any numbers. So we've actually established a very important result. But let's see what happens if we do this with the other vector that we started with, V. So what if, so consider that dot product. And what about this one? What if we do V dot U cross V? So it is very, very similar. The only difference, and this is where I'm going to cheat a little bit. So let's see. Well, I'll see if I can get it to work. Let's see if I can just copy that alone. It's not going to quite work. No, let's not do that. I'll just write it down. So it basically just changed these U's to V's. Everything else stay the same, but U1 there becomes V1, and then I have the quantity U2 V3 minus U3 V2, and then plus V2 times the quantity U3 V1 minus U1 V3 plus U3 times the, V, not U. So V3 times the quantity U1 V2 minus U2 V1. Let's distribute. And again, just look to see, because if this works again, then, what are the odds that lightning will strike at the same point twice? So V1, U2, V3 minus V1, U3, U2 plus V2, U3, V1 minus V2, U1, V3 plus V3, U1, V2 minus V3, U2, U1. All right, so let's see if we can find things that will cancel out. So actually, they're right beside each other. Take a look at this. You got V1, U2, wait, hold on a second. Let's see if that's right. That's V. Oh yeah, it was the way I wrote. Yeah, this one does work because that should be a V. I wrote it and it looked like a U, but this is a V, right? And there you go. So This is V1, U2, V3, and then here we have V1, the U3, V2, and wait, no, that then, okay, let's back up a bit here. Let's make sure that all our letters, yeah, so, okay, so that looks good. So we're looking for something that has a V1 and a U3. This is V3, U2. V2. All right, so let's see. So we have V1 and U2 and V3 and, or U3. Wait, hold on a second. No, V3. And okay, so I think I fixed it now. This is a V. My V's look too much like U's. So that's V. Right, there we go. So V1, U2, V3. And here is its negative. Negative V3, U2, V1. So these cancel out. And then negative V1, U3, V2. Well, again, it's the opposite of that is right here. Here we have the V2, we have the U3, and the V1. So these two cancel out. And then finally, we have the negative V2, U1, V3 cancels out with this. So these two terms are additive inverses, so they cancel out. So yet again, right? So again, what have we done, right? Apart from write a lot of letters. Well, we have our cross product, and then we did the dot product of the cross product and each of our original vectors u and v, and we got in both cases that the dot product is 0. Now remember, when the dot product of two vectors is equal to 0, it means the angle between the two vectors is 90 degrees or pi over 2. That means the two vectors are orthogonal to each other. So the fact that both of these dot products come out to be 0, this implies this really important result. In fact, it is a theorem that we proved, right? So if u and v are vectors in R3 that are non-zero, right? So non-zero, then both u and v are orthogonal to their cross product. So then u and v are orthogonal to the cross product of u and v, right? So that's pretty remarkable. It's like we start with let's say two arbitrary non-zero vectors, and when you compute their cross product, you're going to get a third vector, right? And I want to emphasize that the cross product is a vector, but that third vector is orthogonal to both of these. Note, it's not saying that u and v are orthogonal. No, it is saying that u is orthogonal to u cross v, and v is orthogonal to u cross v. So here is the picture that goes along with this. So for instance, if I have my two vectors, so let's say that's u and this is v. Well, if I take, and again, it could be these vectors could have any angle between them, any angle, and they're not, assuming that they're not pointing in the same direction. But let's say they have some angle that's strictly between 0 and pi, right, or 180. when I compute the cross product, I am going to get a third vector. So it's like I'm in R3, a third vector, where that third vector is at 90 degrees with V and at 90 degrees with U, right? So U cross V, right, would be this vector, right? So this this is an important calculation because there are lots of processes, especially in engineering, where you're given two vectors and you want to find a direction that is 90 degrees or perpendicular or orthogonal to those two given vectors. And the cross product is exactly the calculation that will give us that third direction. All right, so let's do an example with some actual numbers, right? You know, you're probably dying to see some numbers now, apart from subscripts. So let's do an example. And so let's write down 1, -3, 4, and then let's say V is the vector 2, 2, 1, right? So again, nothing particularly important or interesting about these two vectors. These are just two vectors in R3. Let's go through and just compute a couple things, right? So first, let's compute the cross product, right? Since that's what this video is all about. Let's work on finding the cross product of these two vectors. And what I will do, I will set up my 3 by 3 determinant. And you always fill out your first row with the standard unit vectors I, J, K. Then the first vector in your product, its entries go in the second row. And then the second vector in the product, its entries go in the third row. So you fill out your third row with the 2, 2, 1. And then use our cofactor expansion to evaluate this. So this is going to be... And what I'll do is I'll put the number before the I. So again, I'm going to do the blocking out. When I block out the first column in the first row, I'm going to be left with the 3, 4, 2, 1. In fact, yeah, let me write that step just so that since this is our first numeric example of computing the cross product, and then this will multiply the I. So whether you want to put the I in front or after, you could put it after, since that's the way we normally write our vectors using the standard unit vector form. And then minus, the minus is always a part of the cofactor expansion formula. And then for the column with the J, when I remove that column and the first row, I'm left with 1, 4, 2, 1. So 1, 4, 2, 1. Then I have my J there, and then plus, and then finally the column with the K, remove that column and that row, and I'm left with 1, -3, 2, 2. So 1, -3, 2, 2. And then that multiplies the unit vector K. And again, remember, we are getting a vector for our answer. All right. So now we use our 2 by 2 formula for the determinant. And this gives us -3 minus 8, and then times I, and then minus the quantity 1 minus 8 times J, and then the quantity, so plus 2 minus -6 times K. All right, so what do we end up with? -11 I, and then this, so in parentheses I have a -7, but then there's a negative in front of that, making it a +7J, and then 2 minus -6, so that's plus 8K. And if you, so you can leave it in this form, or if you want to write it in the form that's given by the in the problem, then you can write your vector in the angled brackets now, negative 11, comma 7, comma 8, right? Don't mix the brackets and the ijk. It's one or the other, not both, right? So that's the cross product of u and v. Let's, in part B, verify that what we have here, this cross product, this vector, is orthogonal to both u and v. So verify that u and v are orthogonal to u cross v. And how do we do that? That's where we do our dot product, right? So if we take, let's take our u and now do the dot product with the cross product that we just found. So that is, to take the first component of u, that's 1, times our first component of the cross product, which is negative 11, and then plus negative 3 times 7, right? And then finally plus 4 times 8. Let's see what we get here. So we end up having negative 11 minus 21 and then plus 32. And there you go. It cancels out because this is a negative 32 plus 32, so that's 0. Once your dot product is equal to 0, the vectors must be orthogonal, right? So you could say this, or you could actually write it and say that u is orthogonal to u cross v. And then if we do the same thing with v, so v dot this, so if we do this, so again, it's basically the same kind of calculations that we did in the formal proof. Now just use the components of v for the dot product. So take 2 times negative 11 there, and then plus 2 times 7 plus 1 times 8. And then we're going to end up with negative 22 plus 14 plus 8, and there again, everything cancels out. So we have that. So that means v is orthogonal to u cross v, right? So again, I'm just saying that I don't know if u and v are orthogonal. We could check just looking at the components, just doing a quick dot product in my head. I'll just say, I'll make that note and I'll put that in red. Note, since u dot v is not equal to 0, u is not orthogonal to v, right? So the only thing we know for a fact is if you start with two vectors, then take their cross product, then the original vectors will be orthogonal to the cross product. It doesn't say anything about the relationship between the two original vectors. All right. So there's that. And let's do one more. Let's try this. Let's say we switch it. Let's say we find the cross product of v and u. So let's do v cross u. Because we're used to this property as far as doing certain types of products, that the order doesn't matter. But let's switch it up, right? Let's switch it up. And let's put v first and then u second. So let's go ahead and set up our 3x3 determinant. So ijk. And then, so the components of v are 2, 2, and 1. The components of u are 1, -3, and 4. So let's see what happens by switching the order here, right? So we're going to have our 2, 1, -3, 4 times I. So that's when we block out the first column, first row. We're left with that submatrix. and then minus. Block out the middle column first row. We are left with 2, 1, 1, 4. That determinant times j, plus block out the third column, 2, 2, 1, negative 3 times k. All right. And then let's go ahead and, so now our 2 by 2 expansion, so we have 8 minus negative 3, that's times I, and then minus the quantity 8 minus 1, that times j, and then finally negative 6 minus 2, that's times k. So when we simplify, we end up with 11i minus 7j, and then minus 8k, which again we can write using our angled brackets as 11, comma, negative 7, negative 8. Now, look back here at this is u cross v here. So this is u cross v. And then this is v cross u. What do we notice about the relationship between these two? They're actually the one vector is the negative of the other vector. So by changing the order in which we do the cross product, we actually find the vector going in the opposite direction. Because notice that this vector times negative 1 produces this one. And we know whenever we multiply a vector by negative 1, it changes the direction, not the magnitude, right? By negative 1, it only changes the direction, not the magnitude. So I'll just put this as an important note. So you have to be careful when you're doing the cross product. So note that v cross u is actually the negative of u cross v. And this is different. This is, again, there's certain types of objects where when you change the order in which you do the operation, you get a different result. In this case, you get the opposite result. And what we say here is that the cross product is anti-commutative. So we say the cross product of two vectors, so we'll just say the cross product is anti-commutative, right? So we can't change the order and expect to get the same result. In fact, we're going to get the opposite result. So a couple strange things about the cross product, not strange, but just different, but these are things that we want to be aware of. And then coming up in the next video, we're going to look at some more of the geometric properties of the cross product, right? See you then.